Recognizing the shape of a distribution means understanding how values are spread out, where most values cluster, and how extreme values behave. This step matters because many statistical summaries and models quietly assume a certain shape, and if the data do not behave that way, results can become misleading. A distribution shape is usually recognized by looking at a histogram, bars showing how often values occur, a density plot, a smoothed curve, or a simple summary of percentiles, for example, the 25th, 50th, and 75th per fifth percentiles. You are not doing this to make the data pretty. You are doing it to choose summaries and methods that match what the data actually represent. For example, wait times, costs, and counts of visits tend to behave differently from test scores, blood pressure, or heights, even though they are all numeric. A normal distribution is the classic bell-shaped pattern where most values fall near the center and the left and right sides look roughly balanced. Many naturally occurring measurements can look approximately normal when they reflect the sum of many small influences. Examples include adult height in a relatively homogeneous population, many lab values under stable conditions, and some standardized test scores in large groups. In a normal-like shape, the mean average is often a good description of the typical value, and the standard deviation, how spread out values are, is often a useful description of variability. Even then, real data rarely look perfectly normal, so the practical goal is recognizing when the normal approximation is reasonable enough for mean-based summaries and models, not proving perfection. Skewed distributions are very common in applied work. Right skewed means most values are small or moderate, but there is a long tail of large values, which pulls the mean upward. Examples include healthcare cost, length of stay, time to completion for tasks, and time spent waiting in a queue, where a small number of extreme cases can be very large. Left skewed is less common but still occurs, such as when a measure has a hard upper limit and many values cluster near that limit. Examples include a score with a maximum of 100, where many people score in the 90s, or a quality metric where most units perform near perfect compliance and only a few perform poorly. Recognizing skewness helps you avoid summaries that overemphasize extremes, and it also helps you avoid models that assume some symmetric errors when the data are clearly not symmetric. Zero inflated and bounded outcomes are two other shapes that show up constantly. Zero inflated means there are more zeros than a typical count model would expect, often because there are two underlying situations. Some units have no chance of having events, while others have a chance, and sometimes have multiple events. Examples include number of emergency visits in a year, many people have zero, number of defects per batch, many batches have zero, and number of incidents per employee, many employees have zero. Bounded outcomes are variables that cannot go below or above certain limits, such as proportions that must be between 0 and 1, percentages between 0 and 100, or rating scales like 1 to 5. Examples include percent adherence, percent of recommended steps completed, satisfaction scores, and screening coverage rates. Recognizing boundedness matters because the distribution can pile up at the edges, near 0 or near 1, and simple methods that assume the outcome can take any real number can produce predictions that are impossible, like negative percentages or percentages over 100. A practical way to recognize distribution shapes is to look for a few consistent signals. If the mean is noticeably larger than the median, the distribution is often right skewed, and outliers may be influential. If there is a big spike at exactly 0, the outcome likely has zero inflation or a structural reason many observations are 0. If values are stuck between limits, especially with many observations near 0 or near the upper bound, the outcome is bounded and may show floor or ceiling effects. If the distribution has two peaks, it may be bimodal, which can happen when you are mixing two subpopulations, such as two service settings, two severity groups, or two different measurement processes. Recognizing these patterns early sets you up to choose summaries and models that respect what the outcome can realistically look like. Choosing the right summary statistics is about matching the summary to the distribution shape, planetfries, so the summary reflects what is typical and what is important. A summary is a simplified description of a variable, and the goal is to represent the data honestly without being overly sensitive to unusual values. The mean and standard deviation are common because they are familiar, but they are not always the best choice. When the distribution is roughly symmetric and not dominated by extreme values, mean and standard deviation can describe the center and spread well. When the distribution is skewed, heavy-tailed, zero-inflated, or bounded, other summaries usually communicate better. Using the wrong summary can unintentionally mislead, such as making typical experience look worse than it is or hiding how uneven the distribution really is. For approximately normal or symmetric continuous outcomes, the mean is often a reasonable representation of the center, and the standard deviation is often a useful representation of spread. Examples include height, sum lab values, or test scores when there is a fairly balanced spread around a central value. In these cases, reporting mean standard deviation provides a familiar picture. The mean tells where the middle sits, and the standard deviation tells how much variability exists around it. Another useful pair is mean / with a confidence interval for the mean, which communicates uncertainty in the estimated average. Even for symmetric outcomes, it is still useful to check whether a few extreme values are present, because extreme outliers can pull the mean away from the bulk of observations. For skewed continuous outcomes, median and interquartile range are often better summaries. The median is the 50th percentile, meaning half the observations are below it and half are above it, so it is less affected by extreme values. The interquartile range is the distance between the 25th and 75th percentiles, describing the middle half of the data, which gives a stable sense of spread even when there are outliers. Examples where this is common include cost, wait time, length of stay, and turnaround time, where a small number of observations can be extremely large. If you report the mean for these variables, the mean can reflect those extreme values more than the typical experience. A practical comparison often helps. The median might represent what most people experience, while the mean may represent system burden, so reporting both can be valuable when planning resources. For zero-inflated outcomes, summaries should make the zeros visible rather than hiding them inside an average. A single mean count can be hard to interpret when many observations are zero because the mean blends the no events group with the some events group. A useful approach is to report the proportion with zero and then describe the distribution among those with at least one event. Examples include number of emergency visits, number of incidents, number of missed appointments, or number of defects where many people or units have none. For example, you might report percent with zero events, and then report the median and percentiles among those with one or more events. Another helpful summary is percentiles of the full distribution, such as the 50th, 75th, 90th, and 95th percentiles, because that shows concentration of burden. This makes it clear whether the burden is widespread or concentrated among a small high-count group. For bounded outcomes, like proportions and percentages, the summary should respect the bounds and also reflect whether values cluster near the edges. Common summaries include the proportion itself with a confidence interval and sometimes a display of the full distribution across groups or time. Examples include percent vaccinated, percent meeting a quality measure, percent of visits with screening, and adherence percentages. When many values are near 0 or near 100, averages can be misleading because they hide floor or ceiling effects. For example, if most sites are near 100% compliance, but a small number are much lower, the average might look acceptable while masking the low-performing sites. In that case, reporting percentiles across sites or reporting the share of sites below a threshold can be more actionable than only reporting the mean across sites. For categorical and ordinal variables, the natural summaries are counts and percentages in each category. This includes binary variables, multi-category variables, and ordered scales. For example, for a 5-point satisfaction item, reporting the distribution across all 5 response options helps readers see whether responses cluster at the top, spread evenly, or pile up in the middle. Another example, for severity categories, reporting the share in each severity level will helps identify whether the population is mostly low severity or whether a substantial portion is moderate or high. For ordinal variables, additional summaries like the median category or cumulative percentages, such as percent moderate or higher, can be useful when the ordering is meaningful. The key is to avoid treating ordinal scales like true continuous measures unless the interpretation is clearly justified and consistent with how stakeholders understand the scale. Across all types, a helpful habit is to pair a center summary with a spread summary and to choose spread measures that match the shape. For symmetric continuous data, mean and standard deviation work well. For skewed continuous data, median and interquartile range, or median with percentiles, are often better. For count data, mean can be helpful for total burden, but percent with zero path and higher percentiles help reveal concentration. For proportions, the estimate with a confidence interval is a strong standard summary, and percentiles across units can show variation. The goal is not to memorize one set of summaries. The goal is to look at the distribution shape and choose summaries that make the most important features visible without exaggeration. Selecting a model that matches the outcome scale means choosing a modeling approach that respects what values the outcome can take and how the outcome is distributed. A model is a structured way to estimate relationships, but every model comes with expectations about the outcome. If those expectations clash with the outcome scale or shape, the model can give biased estimates, impossible predictions, or uncertainty that looks more confident than it should. The goal is not to pick the most advanced model. The goal is to pick a model whose assumptions align with the outcome. Binary outcomes behave differently than continuous outcomes, and bounded outcomes behave differently than unbounded outcomes. For binary outcomes, models should represent a probability between 0 and 1. Logistic regression is a common choice because it models the log odds of the outcome and ensures predicted probabilities stay within the 0 to 1 range. This makes it appropriate for outcomes like event occurred, completed, readmitted, or passed. Another model sometimes used is a log binomial or modified Poisson approach for estimating risk ratios directly, which can be appealing when the goal is to communicate relative risk rather than odds. The main idea is that binary outcomes need models that treat the outcome as a probability, not as a continuous number. If you use a simple linear model for a binary outcome, it can produce predicted values below 0 or above 1, which is a warning sign that the model does not match the scale. For continuous outcomes that are roughly symmetric and unbounded enough within the observed range, linear regression is often a reasonable starting model. It is used for outcomes like test scores, blood pressure, or other measurements where differences are meaningful and the residuals are not extremely skewed. Another example is average turnaround time, when the distribution is reasonably symmetric after basic cleaning. However, many continuous outcomes are skewed or have heavy tails, such as cost or time measures. In those settings, you can still use regression frameworks, but you often need either a transformation of the outcome or a model family that better matches the distribution. The core idea is that linear regression works best when the noise around the model is roughly symmetric and not dominated by extreme outliers. For skewed continuous outcomes, two common directions are transformation-based modeling or models built for positive skewed data. A typical transformation is the log transformation when the outcome is strictly positive and right skewed, such as cost, length of stay, or time to completion. So modeling the log of the outcome often stabilizes variability and makes the relationship closer to linear. Another direction is using a generalized linear model with an appropriate distribution for positive skew, such as a gamma distribution with a log link. This approach keeps the outcome on its original scale in the data, but uses a model structure that reflects skewness. The practical benefit is that both approaches, like SAT, reduce the influence of extreme values and produce more realistic fitted values. The choice depends on interpretability preferences and how the outcome behaves, especially near 0. For count outcomes, models should respect that values are non-negative integers and that variability often increases as counts increase. Poisson regression is a standard starting point for counts like number of visits, number of incidents, or number of defects. When the data have overdispersion, meaning the variance is larger than the mean, negative binomial regression is often a better fit. Many real count outcomes also require thinking in terms of rates rather than raw counts, because the opportunity for events differs across units. In those cases, models often incorporate an offset term, which adjusts for exposure time or population size, so comparisons are fair. Examples include events per person year, defects per production volume, or incidents per hours worked. Using linear regression for counts can produce negative predictions and can misrepresent the variance pattern, which is another signal that the scale is mismatched. For zero-inflated outcomes, the model choice often depends on whether the extra zeros reflect two underlying processes. One process determines whether someone is at risk for having any events, and another process determines how many events occur among those who are at risk. In that setting, two-part models are commonly used conceptually. One part models the probability of having any events, and the other part models the count among those with events. Variations include hurdle models and zero-inflated count models. The key idea is that a single count model may struggle when there are many more zeros than expected, and separating any versus none from how many among those with some can better match the data structure. Examples include healthcare utilization, where many people never use a service, or defect counts, where many batches have no defects, but a subset have recurring issues. For bounded outcomes like proportions, percentages, and rates that must stay between 0 and 1, model choice should respect those bounds. If the outcome is a proportion based on counts, such as number of successes out of total opportunities, a binomial modeling framework can be appropriate. This includes models that treat the numerator and denominator together, so uncertainty is handled correctly. If the outcome is a continuous proportion with many values near 0 or near 1, specialized approaches like beta regression may be considered, because the beta distribution is defined on 0, 1 and can reflect many shapes. The general lesson is that bounded outcomes can create problems for models that assume the outcome can take any real number, because those models can predict impossible values and can misstate uncertainty near the bounds. Finally, the data structure can change the model choice even when the outcome scale is fixed. If outcomes are repeated over time for the same people or clustered within sites, you need models that account for correlation within units. Mixed effects models and generalized estimating equations are common approaches for this. If outcomes are measured over time as a time series, you may need time series methods that account for autocorrelation and seasonality. These issues are not separate from the outcome scale, they layer on top of it. A binary outcome with repeated measures still needs a binary-friendly model, but also needs a correlation-aware structure. A count outcome across month still needs a count model, but also needs time-aware handling. Matching the model to both the outcome scale and the dependence structure is what makes the analysis credible. When outcomes are skewed, heavy-tailed, zero-inflated, or bounded, you usually have two broad strategies to keep analysis honest. One strategy is to transform the data or choose a model family that naturally matches the distribution. The other strategy is to use methods that are less sensitive to distribution assumptions, called robust methods or non-parametric methods. Both strategies are valid, but they answer slightly different needs. Transformations aim to make the data behave more like what a model expects, which can improve fit and interpretability within that model framework. Robust and non-parametric approaches aim to reduce reliance on strong assumptions, which can be useful when the distribution is messy and you want conclusions that do not depend heavily on a particular mathematical form. Transformations are most common for continuous outcomes with strong right skew, such as cost, time to completion, or length of stay. A log transformation is a classic example. It compresses large values and spreads out small values, making the distribution more symmetric and reducing the influence of extreme outliers. This can make relationships easier to model with tools like linear regression. Another common transformation is the square root, which can help moderate skewness for counts or positive outcomes with smaller ranges. A third common practice is rescaling, such as converting dollars to thousands of dollars or converting days to weeks, which does not change the shape but improves interpretability and coefficient magnitude. The key point is that transformations change the scale you are modeling on, and that changes how results must be interpreted later. Transformations can also be applied through model choice, rather than literally changing the data. For example, if a positive continuous outcome is skewed, you can use a generalized linear model with a gamma distribution and a log link, which effectively treats relationships on a multiplicative scale without needing to manually transform the outcome. For count outcomes, Poisson or negative binomial models are distribution-matched approaches that behave like a built-in transformation because they assume non-negative integer outcomes with a variance pattern DESI that grows with the mean. For bounded outcomes like proportions, binomial models, or other bounded outcome approaches, respect the outcome limits directly rather than forcing the outcome into a normal framework. This is still in the transformation family of thinking because you are matching model assumptions to outcome shape, just in a more direct and principled way. Robust methods are useful when outliers or heavy tails are the main issue. Or when you want estimates that are less influenced by extreme values. One robust approach is to summarize with medians and interquartile ranges rather than means and standard deviations, because medians are not pulled by extremes. Another robust approach is to use regression methods that downweight outliers or use robust standard errors, which can provide more reliable uncertainty estimates when model assumptions are imperfect. Another robust direction is quantile regression, which models a percentile of the outcome, like the median, rather than the mean. This is especially useful when stakeholders care about typical experience or the upper tail separately. For example, modeling the 90th percentile of wait time can directly address long delays, which can be more operationally relevant than the average. Non-parametric methods are useful when you want comparisons that do not rely on a normality assumption or when outcomes are ordinal or heavily skewed. For two-group comparisons of continuous outcomes, rank-based tests like the Wilcoxon rank sum test compare distributions in a way that is less sensitive to extreme values and skewness. For paired comparisons, rank-based alternatives exist as well. For comparing more than two groups, Kruskal-Wallis is a common non-parametric approach. For association measures, like rank-based correlations like Spearman correlation, capture monotonic relationships without assuming linearity. These methods often answer questions about relative ranking or distribution shifts, rather than differences in means. That can be an advantage when the mean is not a stable or meaningful summary, but it also means the effect size interpretation is different and should be communicated carefully. Choosing between transformation-based strategies and robust non-parametric strategies often comes down to what you need from the result. If you need a model that produces adjusted estimates, predicted values, and interpretable effect sizes within a multivariable framework, transformations or distribution-matched models are often the more flexible path. If you mainly need a defensible comparison that is not sensitive to outliers and adjustment is minimal or not required, non-parametric tests can be a clean choice. Robust regression approaches sit in the middle. They allow multivariable adjustment but reduce sensitivity to outliers. Examples clarify the trade-offs. If cost is highly skewed and you need adjusted comparisons across groups, a log scale model or gamma model is usually more practical than a non-parametric test. If a small data set has extreme outliers and you only need a simple group comparison, a rank-based test can be more reliable than forcing a transformation that still leaves instability. Finally, it is common to use both perspectives to build confidence. A transformation-based model can be your primary approach when it aligns with the outcome scale and the decision need. A robust or non-parametric check can serve as a sensitivity analysis to see whether the main conclusion depends heavily on a few extreme values or on distribution assumptions. For example, you might model log cost and also compare median costs across groups, checking whether both point in the same direction. You might model counts with a negative binomial approach and also report percent with 0 and upper percentiles, checking whether the story matches. Using both thoughtfully keeps interpretation grounded. The model provides a structured estimate, and the robust summaries provide a reality check. When you analyze data on a transformed scale, the model is describing relationships in the transformed units, not in the original units that people naturally think in. The main skill is translating results back into plain language on the original scale without changing what the model actually estimated. This matters because transformed scale results can be easy to misstate. For example, a coefficient from a log transformed outcome thing is not an extra number of days or an extra dollars in a direct additive sense. It often represents a multiplicative change, like a percent change or a ratio. Another example is that differences on an arcsine or logit scale for proportions do not translate into constant percentage point differences across the range. The meaning can vary depending on the baseline level. The goal is to keep your interpretation aligned with the transformation Weserle, so the result is accurate and usable. Log transformations are the most common, so it helps to build a stable interpretation habit for them. If you model the logarithm of a positive outcome, like cost or time, the coefficients often correspond to relative differences. In plain language, that means how many times larger or what percent higher or lower, rather than how many units higher. For example, if you compare two groups on log cost, you are often estimating a ratio of typical costs, which can be described as Group A has about X percent higher cost than Group B, depending on the coefficient size. Another example, if you model log wait time, a coefficient can represent that one group tends to have wait times that are proportionally larger, which is often more realistic than assuming a constant additive increase in minutes across the entire range. A third example, if you model log length of stay, interpretation becomes about percent change in stay length rather than a fixed number of days, which often fits how stays behave because longer stays tend to have more variability. Interpreting transformed results correctly also requires understanding that summaries on the transformed scale often map to different typical quantities on the original scale. A common example is that the mean of log values corresponds to a geometric mean on the original scale, not the arithmetic mean. The geometric mean is a multiplicative center and is often a better typical measure for right-skewed outcomes. For example, if costs are highly skewed, the geometric mean can represent typical costs without being dominated by a few extremely high cases. Another example, for time measures like turnaround time, the geometric mean can be more stable than the arithmetic mean. A third example, if you compare groups using a model on the log scale, you are typically comparing those multiplicative centers, which is why the natural interpretation is ratios and percent differences rather than raw differences. Transformations like square root are often used to reduce skewness for counts or positive outcomes where log is not ideal, especially when values include zeros. Interpreting square root transformed models is less intuitive in plain language because the relationship is not purely additive or purely multiplicative on the original scale. The practical approach is to avoid over-interpreting the raw coefficient and instead translate the implication back to the original scale using predicted values at meaningful points. For example, rather than stating a 1 unit increase leads to 0.3 increase in square root outcome, you would describe what the model implies for expected counts at relevant predictor values. Another example is that square root transformation can stabilize variance in a way that supports modeling, but the translation back to original units usually benefits from focusing on differences in predicted outcomes rather than the coefficient alone. This is a common reason analysts lean toward models that are naturally aligned with counts rather than transforming counts into a quasi-continuous scale. For bounded outcomes, transformations like logit or arcsine square root have historically been used to make proportions more normal-like, but interpretation becomes tricky because the transformed scale is far from intuitive. In practice, a more teachable interpretation approach is to translate model results into predicted probabilities or predicted percentages on the original scale. For example, if a model is fit on the logit scale, the clearest communication is usually predicted probability for group A is X% and for group B is Y%, possibly with a difference in percentage points and a confidence interval. Another example, if the outcome is a rate or proportion that is near 0 or near 1, small changes on the transformed scale can correspond to very different percentage point changes, depending on where you start. That is why it is safer to communicate effects as predicted probabilities at meaningful baseline levels rather than implying a constant effect across the range. A frequent interpretation pitfall on transformed scales is mixing up percent change with percentage point change. Percent change is relative, meaning it is a fraction of the baseline, while percentage point change is absolute. For example, moving from 10% to 20% is a 10 percentage point increase, but a 100% increase relative to the baseline. Moving from 50% to 60% is also a 10 percentage point increase, but only a 20% relative increase. On log-type interpretations, you are usually in the world of relative change, which can accidentally be miscommunicated as an absolute change. Multiple examples show why this matters. A 20% relative reduction from 50% is a 10 percentage point decrease, but a 20% relative reduction from 10% is a 2 percentage point decrease. If you communicate one as the other, stakeholders can misjudge effect size substantially. Finally, transformed scale interpretation is strongest when you tie it back to realistic examples using predicted values. The safest habit is to communicate in original units, predicted costs in dollars, predicted times in minutes, predicted probabilities in percentages, and predicted counts per unit time. You can still be faithful to the transformed model while translating output into understandable quantities. For example, if the model is on the log scale, you can communicate the ratio and also provide an example. If the typical value is around 100 units in one group, the model implies around 120 units in the other group, which grounds the multiplicative relationship. Another example, for a logit-based model, you can communicate predicted probabilities for common scenarios rather than reporting an odds ratio alone. This approach keeps results accurate, reduces confusion, and makes the analysis portable across jobs and settings because the interpretation stays anchored in the scale that people use for decisions.